Hey everyone, welcome back to the deep dive. You're here because you like getting to the bottom of things, right? You want to understand how stuff really works.
That's right. No time for fluff, just getting into the core ideas. And today, well, we're going deep on something pretty amazing, something that's right at the heart of robotics and AI. How do you get like a smart
Big
machine?
robot, you mean?
Yeah, robot. Or a self-driving car, or even think of a really sophisticated piece of software. How do you get that from point A to point B, but intelligently, not just a straight line,
Mhm.
right? Avoiding obstacles, figuring out the best way, it's a whole problem in itself. We call it path planning.
And the stuff we're looking at today, it takes a really new approach to this whole path planning thing, using what's called reinforcement learning, RL.
RL, yeah, powerful stuff.
And specifically, we're going to be digging into a research paper that explores three, I guess you could say, cutting-edge RL techniques. They're called deep Q learning. We'll call it DQN for short. Proximal policy optimization, PPO. And then there's deep deterministic policy gradient, DDPG. Bit of a mouthful, those names.
So they do love their acronyms, don't they? But it's
Yeah.
all really fascinating stuff, I promise.
Okay, so what we want to do today is figure out why the old school ways of doing path planning, why they run into trouble when you get to the real world where things are, messy.
Exactly, yeah.
And then we'll see how these three RL methods can offer, well, potentially some really cool solutions. We'll look at how each one works, what it's good at, where it might fall short, and, the most important thing, when you want to use one versus the others. Sound good?
Sounds like a plan.
All right, so let's jump right in. Why do these tried and true methods for path planning, why do they kind of hit a wall when things get complicated in the real world?
Yeah. The paper we're looking at, it brings up a few key problems. Let's take a drone delivering a package in a city, right? Busy city.
Lots going on.
Right, exactly. It's not flying in some empty space. You got other drones, birds, maybe even, a crane pops up from a construction site. Traditional methods, they often have trouble adapting in real time to these moving obstacles.
Dynamic, yeah.
Yeah, dynamic obstacles. And to keep recalculating the route all the time, it just becomes too much computationally.
So it's like planning a route when everything's standing still, that's one thing. But when the whole environment's changing around you all the time, that's a whole other story.
Exactly. And then there's just the sheer volume of information that a robot might have to deal with. Think about that self-driving car, right?
Mm-hmm.
It's getting data from cameras, LiDAR, radar, all this sensory input all the time. This creates what's called a high-dimensional state space. It's basically a fancy way of saying there's just a ton of information to process. And traditional methods, they have a hard time building an accurate model of a complex environment like that.
So they can't really plan a path well because they can't even make sense of all that information.
Right. It's like trying to solve a maze when you can only see a tiny bit of the walls at any given time.
Okay, so like trying to navigate a crowded marketplace in the dark, but the stalls and the people are all moving around.
Exactly. You got it. And then there's this thing called nonlinear dynamics and uncertainty. It basically means that the way things move in the real world, it's not always predictable.
Like a ball bouncing?
Yeah, exactly like that. Tiny changes in the initial throw, it ends up somewhere totally different. Or like a gust of wind messing with a drone. Or a car swerving. And the old algorithms, they often rely on these rigid set models. They struggle with that randomness, with that uncertainty.
Okay, so the real world is messy. It's unpredictable. So that brings us to reinforcement learning. Give us the high-level view. What is RL all about?
At its core, RL is about teaching an agent, and by agent, we just mean our robot or car or software, teaching it to make decisions by letting it interact with its environment and then learn from the consequences. Like, imagine training a bot to play a video game.
Okay, yeah.
It takes actions, right? And then based on what happens, does it get a reward? Like, did it reach a goal? Or a penalty? Did it run into something? It learns to adjust its behavior to try and get more rewards over time.
So it's like learning by doing, learning through trial and error, which sounds like it would be perfect for dealing with these complex, changing environments we were just talking about.
Exactly. Unlike traditional methods that need specific instructions or a complete map of everything, an RL agent can adapt. It can find good paths, even in situations it's never seen before. And the paper we're looking at, it emphasizes this really important aspect of RL, the balance between exploration, trying new things, seeing what works, and exploitation, sticking with what's already working well.
So it's like a trade-off.
Yeah, exactly. And that back and forth between exploring and exploiting, that's key to making RL work in these complex environments.
Okay, so the robot's constantly testing the waters, seeing what gets it closer to its goal and what gets it into trouble. Let's get some of the terms straight. What exactly do state, action, and reward mean in this context?
Okay, so state is basically the agent's current situation, like a snapshot of everything going on. For our delivery drone, the state might be its GPS coordinates, its speed, maybe even what its camera sees around it. Action is what the agent can do. For the drone, that might be speed up, slow down, change direction. These actions can be simple choices like up, down, left, right, or they can be more complex like a specific steering angle and speed for a car. And then reward is the feedback. If an action helps the agent reach its goal or avoid an obstacle, that's a positive reward. If it crashes or moves further from its destination, that's a negative reward.
Got it. State is, where am I and what's going on? Action is, what can I do next? And reward is, was that a good move? Let's get into the first RL technique, Deep Q learning, or DQN. What makes this one interesting for path planning?
Well, DQN builds on this idea called Q learning, which is all about learning the best action to take in any given situation. But DQN takes it to another level by using deep neural networks. Think of them as really complex mathematical functions that can process lots of data.
So the deep part refers to those neural networks.
Exactly, like a sophisticated filter that can take in all that raw censored data camera images, LiDAR readings, and figure out what's important for making good decisions without us needing to program it explicitly. This is what lets DQN handle those high-dimensional state spaces we were talking about, which is why it's used in things like autonomous driving and drone navigation.
So it can deal with all that sensory information. Now, the paper also mentioned experience replay and target networks. What are those and why are they important for DQN?
Those are clever techniques that help to stabilize the learning process. Experience replay is like a memory bank for the agent. It stores all its past experiences, where it was, what it did, what reward it got, and then during training, it randomly pulls out a bunch of these past experiences and learns from them. This helps to make the learning process more stable and less likely to get stuck in a rut. And target networks, well, they're kind of like a copy of the main neural network, but they update more slowly. This also helps to prevent things from getting too erratic and keeps the learning process on track. Oh, and the paper also mentioned this thing called prioritized experience replay. Basically, it makes the agent learn more from the experiences that were really surprising or informative.
So it's not just learning from all its past experiences equally, but focusing on the ones that were really important. Makes sense. So what are the big pros of using DQN for path planning?
Two big advantages come to mind. First, as we said, DQN can handle those complex, high-dimensional state spaces. That's crucial for robots in the real world. And second, DQN is very scalable. Unlike earlier versions of Q learning, we can use it for much bigger and more complex environments.
That's huge. But what about the downsides? Where does DQN struggle?
Well, one issue is training instability. Those neural networks can be a bit finicky. Sometimes they have trouble generalizing to new situations, or the target networks don't update properly, and the whole learning process becomes unstable. The other big issue is data efficiency. DQN needs a ton of data to learn effectively. Think of a self-driving car learning with DQN. It might need to experience countless near misses or even accidents, at least in a simulation, to truly learn how to navigate safely. And that's a problem, right? Because collecting that much real-world data is expensive, time-consuming, and potentially risky.
So DQN can handle a lot of information, but it needs a lot of practice, and sometimes it's a bit of a drama queen. Let's move on to our next contender, PPO. What makes this one stand out?
PPO takes a slightly different approach compared to DQN. Instead of focusing on learning the value of actions, PPO tries to directly optimize the policy, the strategy the agent uses to choose actions. This makes it really good for environments where the actions are continuous, like steering a car. It's also great for high-dimensional environments.
And the paper really highlighted how well it performs in dynamic environments, like a busy street with lots of cars and people moving around. What makes it so good at that?
One of the key innovations in PPO is something called a clipped objective function. It's a mechanism that limits how much the policy can change at each step during training. This helps to stabilize the learning process. So in a dynamic environment where things are constantly changing, PPO can still learn effectively without the learning process going haywire.
So small, controlled adjustments rather than huge, jerky movements. Sounds sensible when you're trying to avoid those unexpected obstacles. What are the big pros of using PPO for path planning?
Well, we've already talked about stable learning, thanks to that clipped objective function. Another big plus is that it can handle both continuous and discrete actions, so it's quite versatile. And it's proven itself to be effective in complex dynamic environments, making it a strong candidate for real-world applications.
Okay, so it's a versatile and stable learner. That sounds pretty good. But where might PPO struggle?
The main drawbacks are its computational intensity and its sample efficiency. PPO can be quite resource hungry. It needs a lot of computing power to optimize the policy, especially when dealing with high-dimensional data. And although it's generally better than some other methods, it can still need a lot of interaction with the environment to learn well.
So it's good in tough situations, but it could be a bit of a resource hog and needs a fair bit of practice. All right, let's move on to our last RL technique, DDPG. What's the story with this one?
DDPG. It's called an actor-critic algorithm, and it's specifically designed for environments with continuous actions. It's like it takes the best of both worlds, combining the strengths of value-based methods like Q-learning and policy-based methods like PPO. It uses two neural networks. An actor network learns the policy, the best action to take in a given situation, and a critic network learns the value function, basically how good it is to be in a certain state and take a certain action. And because the actor learns a deterministic policy, meaning it outputs a specific action, it's great for tasks that need precise, continuous control.
So it's like having a pilot, the actor, and a co-pilot, the critic, working together, with the critic constantly evaluating the pilot's decisions. How does this help with path planning in complex environments?
It helps a lot, actually. Having a separate critic that's always evaluating helps the actor refine its policy much more effectively. And just like DQN, DDPG uses those techniques we talked about, experience replay and target networks, to stabilize the learning process. That's really important for complex environments.
So DDPG has this evaluation system, and it borrows some stabilizing techniques from DQN. What are the pros of using it for path planning?
Its biggest strength is definitely its ability to handle continuous action spaces. This makes it perfect for tasks that need fine control, like steering a car smoothly or controlling a robot arm with precision. The actor-critic framework also tends to lead to more stable learning, and like DQN, it can handle complex, high-dimensional environments, making it well-suited for things like robots and autonomous vehicles.
Sounds like it could be the perfect choice for really precise robotic control. But what are the cons that we need to watch out for?
Well, training DDPG can be quite sensitive. If the parameters aren't set just right, it can be unstable. For example, the critic might overestimate the value of certain actions, and the actor might learn a bad policy. Another issue is exploration. Because DDPG learns a specific action for each situation, it can sometimes get stuck and miss out on better solutions. To counter this, researchers often add some random noise during training to force it to explore more. And finally, just like other methods we've talked about, it can be computationally expensive and require a lot of data.
So it's great for precision in complex environments, but it can be a bit of a diva to train. Now, let's compare all three. The paper talked about the balance between exploration and exploitation, right? How does each algorithm handle that?
Right. Remember, exploration is about trying new things, and exploitation is about sticking with what works. DQN, with its experience replay, can explore a bit by learning from a mix of past experiences. But since it usually works with discrete actions, its exploration is limited to those specific actions. PPO uses a stochastic policy, meaning it introduces some randomness into its action choices, which helps with exploration. And DDPG, with its deterministic policy, has the biggest challenge with exploration. It often relies on adding external noise to its actions to encourage it to try new things.
So they each have their own way of finding that balance.
Yeah.
And the paper also emphasized that training these algorithms is tricky, and the parameters you set, the hyperparameters, are crucial. Can you tell us a little bit more about that?
For sure. Each algorithm has its own set of hyperparameters that you really need to fine-tune. For DQN, things like the size of that experience replay buffer, how much data it learns from at once, how often the target networks are updated, those are all important. For PPO, it's things like how much the policy can change at each step, the learning rate, and how much randomness is added to encourage exploration. And for DDPG, it's the learning rates for the actor and critic, the parameters for that exploration noise, and how the target networks are updated. Getting these hyperparameters right is crucial. If they're off, the training can become unstable, or the algorithm might learn very slowly, or it might even learn a bad policy that doesn't work well.
It sounds like quite an art to get these things to learn properly. So let's talk about how these techniques are actually being used. What are some examples of real-world applications for DQN, PPO, and DDPG in path planning?
DQN, with its ability to handle discrete actions and lots of sensory input, is often used in things like navigating in warehouses with robots or for finding paths in simple road networks. You even see it in video games for controlling AI characters. However, because it works with discrete actions, it's not ideal for tasks that need smooth, continuous control like steering. PPO, on the other hand, is really good at handling continuous actions in dynamic environments. So it's a good choice for things like drone navigation, self-driving cars in traffic, and general robot path planning in unpredictable environments. DDPG is best for continuous control tasks that need very precise movements. Think things like controlling robotic arms or making a self-driving car accelerate and brake smoothly. It's also used in robotics for things like walking and running. But as we said, it can be tough to get it to explore properly, and the training can be sensitive. Now, one thing to keep in mind is that all these RL methods, they need a lot of computing power and data to work well. That can be a problem for real-world applications. Think about training a self-driving car with RL. You can't really have it driving around in the real world and potentially causing accidents while it's still learning. So a lot of the training has to happen in simulation, which isn't always perfect.
So each technique has its own strengths, and the best choice depends on the specific application. Okay, let's wrap things up. What are the key takeaways here for our listeners? What are the strengths and weaknesses of each approach?
So, the recap. DQN is good for discrete actions and can handle lots of sensory information, but it can be hard to train and needs lots of data. PPO is more stable, can handle both continuous and discrete actions, and works well in dynamic environments, but it requires a lot of computing power. And DDPG is great for precise, continuous control in complex environments, but it can be tricky to get it to explore properly, and the training can be a bit sensitive.
So choosing the right algorithm depends on the task. You have to consider how complex the environment is, what kind of actions the agent needs to take, and how much computing power you have available.
Exactly. RL is a powerful tool for path planning, but it has its challenges. Researchers are working on ways to make these algorithms more efficient, so they need less data and computing power.
Well, this has been a really fascinating look at RL for path planning. It's a complex topic, but hopefully our listeners now have a better understanding of the basics and how these different algorithms work.
I hope so too, and it really makes you think about the future, doesn't it? Knowing what we know now about DQN, PPO, and DDPG, what kind of future applications of autonomous systems get you excited? Or maybe even a little bit worried? Something to think about.
That's a great question to leave our listeners with. Thanks for joining us for another deep dive. We'll see you next time.